Continuing off the person before me, now I'm doing type 4, predicting precipitate. Now, say that you were given this type of question. If 15 milliliters of 0.024 molar lead nitrate is mixed with 30 milliliters of 0.03 molar potassium chromate, will it precipitate form? Now, it's important when looking at this question to have a type of format laid out before you so that you know which steps to take before which ones. So here, we're going to start off with step 1, determining the sparingly soluble salt by using the solubility chart. Before we do that, you write the net ionic equation for this type of question, and then from there you can determine it. Step 2, write the net ionic equation and state the correct KSP expression for the salt that you found. Step 3, determine the QSP value by finding the dilution concentration. Step 4, if QSP is larger than KSP, there is precipitate. If QSP is smaller or equal to KSP, there is no precipitate. And if it's precipitate, if there's a precipitate, then it's supersaturated solution. If there isn't, then it's saturated or unsaturated. Now, we move on to an actual question that we can apply these steps to. Say that you were given a question, a solution containing lead-2 nitrate is mixed with one containing sodium bromide to form a solution that is 0.015 molar in PbNO3 and 0.0035 molar in NaBr. Does it precipitate form in the solution? So first, we write out the ionic equation for this question. You should know how to do this. If you do not know how to do this, go back to grade 11. Now that you have the net ionic equation and you've balanced it, you can look at the solubility chart. Solubility chart tells us that PB has a low solubility while NO3 has a high solubility. Solubility chart shows that NO3 is very soluble, whereas PB is combined with Br to become insoluble, or in other words, to become a precipitate. So the sparingly soluble salt is PbBr2. Step 2, write the net ionic equation and state the correct KSP expression. So you're going to write the ionic equation for this salt that was found. You write it, you balance it, and then for the KSP, you write the two products, and then the 2 becomes a power. Now, step 3. Determine the QSP value by finding the dilution concentration. And you do that by using the C1V1 equals C2V2. And here you're looking for C2. So, you do 0.015 molar, which was given here, multiplied by 10 milliliters divided by 40 milliliters, which equals that number. Now let me explain what this equation is. So here you have the initial concentration. You multiply it by how much was in, how much of the concentration did you put inside, then divide it by the total amount that's inside the cup, which will give you the dilution concentration before the reaction took place. You do that for PB and for Br. Do the same thing for Br. And then for the QSP, it's the same way of organizing it. So once you have that equation, QSP equals PB2 and then Br2, you actually just put in the numbers in here, and then you get 2.58 times 10 to the negative 8, which is your QSP. Now, if QSP is bigger than KSP, there is precipitate. If QSP is smaller or equal to KSP, there is no precipitate. And then you can see the KSP of lead bromide or PbBr2 on your KSP chart, which says that PbBr2 is 6.6 times 10 to the power of negative 6, which is smaller than 2.58 times 10 to the negative 8, which proves that there's no precipitate that occurs in this type of reaction. Type 5, common ion effect. If you want to have more MgF2, add a chemical that has a common ion so that precipitate can be produced. If the solution has the same common ion, for example F, then as Le Chatelier's principle states, the reaction will move to the left side so that equilibrium can be established. Now, let me help you visualize this. You have an equation like this, for example, and you want to add NaF. Since right here you have a common ion, it's going to be in favor of this one. So the reaction is going to move towards this way. But you can also say that NaF also favors the product side. But as Le Chatelier's principle states that if the product side is unbalanced, then the reaction will move towards the left side, so causing the reactant to shift to MgF2. And that's how you make it that's how you add a common ion so that you can favor one side or the other. Okay, so maybe you'll understand it better if it's given in an actual question. So say that you are given a question like this. Calculate the solubility of MgF2 in a solution of 0.08 molar NaF. And you're also told that the KSP is equal to 7.4 times 10 to the power of negative 11. First thing that we do, as always, is make the MgF the net ionic equation for MgF, which is that right there. Yeah, you balance the equation, and then you do the ice table. Ice table is going to help us to find the KSP expression. So, as we know, we ignore the MgF2 because it's solid. It was never mentioned any initial for Mg, but here's the interesting part. That's where we come into common ion. It gave us here that NaF has a concentration of 0.08. NaF has a common ion with the product F, which is fluorine. It has fluorine here, and this one has fluorine. And we know that concentration, it's constant, so it doesn't change if you break a chemical apart. So it's not going to change if you split Na and then you make it into Na and then plus F. It's always going to stay the same. So the initial for F is 0.08. Now for change, you don't have anything for MgF2. You don't for Mg you have just X because it's 1, and then for this one it's 2X because you have 2, obviously. For E you just add them up, and then KSP, you make the KSP expression, you plug in the numbers. So you plugged in KSP, which equals X X multiplied by 0.08 plus 2X to the power of 2. Now, since this number is so small, you can basically consider this number insignificant because it's going to be 0.00000 until infinity, basically. So you can just ignore this and cross it out. So what it becomes is 7.4 times 10 to the power of negative 11, which equals 6.4 times 10 to the power of 3x, because you multiply this one with that one and then square it, which gives you that. Then you divide it by each other, which will give you 1.17 times 10 to the power of negative 8. Now to test comprehension. So please pause the video now and try to solve these questions. The answer will be given in 3, 2, 1. So, the way that you solve this question, oopsie, I forgot to put the pointer. Okay, so the way that you solve this question is to do the KEQ equation, which is the same as KSP. All you do is divide the product by the reaction. It says here that the product is 0.04 and the reaction is 0.03. Divide them by each other, you'll get 1.3. For this question, what will cause a shift in the equilibrium? Now, the reason why it's changing temperature and not any other one is because here you're given H, which is negative 41, which means it's an exothermic reaction, which means that the energy is in the product. Now, if you change the temperature in the product side, where will the reaction have to shift to balance out? To the left side. And that's the answer for the multiple choice. Now, the word problems. Again, please pause the video and try to solve this word problem by yourself. Here is the answer. So the way that you solve this problem is by making the net ionic equation for this one plus this. And then from there, you look at the solubility chart to see which one would actually work out. Ca is the one that works out. So then you expand Ca. You do the net ionic equation for Ca. Then you do the dilution for both. You get a KSP. You get a QSP, which equals to 1.8 times 10 to the power of negative 3. Second word problem. What is the molarity of a saturated solution of MgOH2? The KSP is 1.8 times 10 to the negative 11. Molarity means concentration. So you're finding concentration when you're given KSP. Pause the video and try to answer it now. Okay, so what you do, like always, write the net ionic equation. You wrote it down, then you do the ice table for this one. This is all Na because it's solid. Then Mg, it's also 0 because it's never mentioned for Mg. And OH, it's also 0. For C, for the change, it's 1 to 1 to 2. So it's basically minus x, and then 2x. And then you're left here with x and 2x. You write the KSP expression, which is that right there. Then you basically fill in algebra. I don't think I need to explain how to do algebra for you guys. And you get the molarity of 4.308 times 10 to the negative 4 moles. Now, things to look out for when solving these type of questions. When solving word problems, look for keywords, like I said in the beginning of my presentation. Or actually, I'm not sure if I said it. I might have erased that video. I'm not sure. Such as initial or saturated keywords. These two keywords can really help you. Initial and saturated. Initial is telling you basically that you're solving for QSP. Or you're solving for QSP. Saturated means that you're solving an equilibrium problem. This will help you decide which method to use to solve the problem. Try and understand the concepts of how you would solve KSP questions and QSP. If you understand the format, then questions regarding those two won't be difficult. Thank you so much for listening to my amazing presentation, and have a good weekend. And yeah.